This is the first of 3 videos dealing with sound in Chapter 17. 3 categories of sound. We can think of sound from a human perspective as to what we're able to hear with our ears, and that generally is between the range of about 20 hertz to 20 kilohertz. That's what we call the audible range. For human beings, that's what's been established as what we need to survive, and so it's a relatively broad range, but not as broad as some other creatures in the animal world. If we go above the audible range, we would be into the ultrasonic, ultra meaning above the sonic range. And if we went below the audible range, we'd be in the infrasonic, infra meaning below the sonic range. So there are some creatures that can listen above the above the audible range. Dogs, you have the dog whistle, so you can hit a frequency that humans can't hear, but dogs can hear. Or bats actually fly in the ultrasonic range, using that to actually see, in a sense. And the infrasonic, some creatures like elephants, they have the large ears to pick up very low intensity sounds, but they also are listening at frequencies way down to about 3 or 4 hertz. And some of the researchers who have studied elephants have seen that they actually communicate down at these very low frequencies, 3 or 4 hertz. So that's kind of an interesting aspect of the human and animal world. In general, the equation for the speed of sound in any medium is some elastic property of the medium divided by some inertial property of the medium, square root. So the velocity of sound is the square root of elastic over inertial. For instance, in a liquid, the velocity of sound is the square root of the bulk modulus of the liquid divided by the density of the liquid. So the density being the inertial property, bulk modulus, the elastic property. For a solid, it is the square root of the Young's modulus of the solid divided by the density of the solid. For a string, which is a one-dimensional solid, it is the tension of the string divided by the one-dimensional density, which is the mass per length of the string, square root. And for a gas, it is the adiabatic bulk modulus divided by the density of the gas, square root. Adiabatic bulk modulus has a factor, a gamma in there, which pretty well designates whether the gas is monatomic or diatomic or triatomic, polyatomic, and that has influence on the distribution of energy and the speed of sound. So it's kind of interesting that they all have a similar relationship, elastic over inertial, square root. We can prove this one-dimensional string equation from the general equation for velocity of sound in a solid being the square root of Young's modulus over density. If you recall from Physics 1, the Young's modulus is the stress over the strain, and so if we had a one-dimensional solid like a string, the stress would be the tension, the force of tension over the cross-sectional area of the string, and then we have the strain, which is the change in length over the original length. So we have stress over strain. The density of the string is the mass over the volume being the length, the change in length times the cross-sectional area for a cylinder like a string. With a little bit of algebra here, the areas cancel out and the delta L's cancel out, and we are left with the square root of tension divided by mass divided by length, which is indeed the linear mass density, mu. So it's the square root of tension divided by mu. And that's for a one-dimensional solid like a string, but it is derived from just solids in general. So kind of a neat little equation. Let's try this out with a liquid. Let's find the speed of sound in mercury which has a bulk modulus of approximately 2.8 times 10 to the 10 newtons per meter squared, and a density of 13,600 kilograms per meter cubed. Well, the velocity of sound in a liquid is equal to the square root of its bulk modulus over its density. So for mercury, that would be 2.8 times 10 to the 10 meters per second over 13,600 kilograms per meter cubed, square root. That's 1,430 meters per second. So the speed of sound in mercury is a little bit more than 3 times the speed of sound in air. The speed of sound in air is 343 meters per second. So if you're listening for sound in air, that's how fast it would travel. If you were to, say, dip your head in mercury, it would travel actually more than 3 times faster. And so you would hear it 3 times faster. That could be an advantage, except you don't want to go around dipping your head in mercury. So please don't do what I suggest. Not good for you. Speed of sound in various media. We just said that the speed of sound in air at room temperature, 343 meters per second. That's going to be a number you want to memorize because we're going to use it over and over again. And that's just a basic number. At room temperature, speed of sound, 343 meters per second. In water, it is 1,493 meters per second, so more than 3 times the speed of sound in air. It travels faster. So if you were at a lake, and somebody were working on a dock on the other side of the lake, you could hear the sound of that pounding of the hammer faster if you were to listen in the water as opposed to listening in the air. Copper. A solid like copper, speed of sound is 5,010 meters per second. So much faster. It has to do with the fact that the structure is more organized in a medium like copper, where it can be transported from electrons to electrons through the medium much faster. So the speed of sound is much faster in a good solid than it is, say, in air or even in a liquid like water. Speed of sound also depends on the Celsius temperature. In particular, for a gas like air, the velocity of sound is 331.5 meters per second times the square root of 1 plus the temperature in Celsius divided by 273 degrees Celsius. Now, for most applications that we would have, the temperature in Celsius is going to be a pretty small number. I mean, room temperature is 20 degrees Celsius. Freezing outside would be 0 degrees Celsius. So we're talking a range for our normal being of about 0 to 40 degrees Celsius. So this T sub C is going to be a relatively small number compared to 273. Why am I talking about this? That means that this fraction, T sub C over 273, is going to be a small number compared to 1. So we can think of this as 1 plus x to the 1/2 power. And if we were to expand that by the binomial expansion just to the first order term, because x is so small, then we can make an approximation for this square root and say that it's actually about, the velocity of sound is about 331, 1 plus this fraction, T sub C over 273, to the 1/2 power. First order approximation is to bring that power down, and that's approximately equal to 331, 1 plus 0.5 for the square root times x, T sub C over 273. So the velocity of sound is approximately, for this range, 331 plus 0.6 times the temperature in Celsius. Very cool result. So at room temperature, where the temperature is 20 degrees Celsius, the velocity of sound is 331 plus 0.6 times 20, which is 12, so it's 343 meters per second. At 0 degrees Celsius, freezing, the speed of sound would simply be 331 meters per second, so a little bit slower. Why slower? As the temperature goes up, the air molecules are moving around more, and they're interacting more, and hence they can exchange the energy of the sound wave faster than if they're slowed down. So as temperature goes up, sound will travel faster because the interaction is faster. Sound is a pressure wave. If I were to take a piston and create a disturbance so that I can cause a condensation of the air as I push it in and a rarefaction, a little slight vacuum as I pull it out, I can create a wave, a pressure wave, where I have condensation and rarefaction in succession. And this pressure wave travels through the air, eventually hits your eardrum, moves your eardrum back and forth, and then your brain interprets that movement as a frequency, and that frequency as sound. So, if you didn't have air as a medium to transport this pressure wave that will affect your eardrum, don't check your sound. I'm just saying that you would not be able to hear a word I'm saying if we didn't have air. So we need air to transmit this sound to move our eardrum so that we can interpret sound. So the phrase, nobody can hear you scream in space, is true. In space, no one can hear you scream, which is the motto after the first Alien movie. But it's true, because if you're in space, there'd be no air and you wouldn't be able to hear the sound. I think that kind of meant that you were alone in space and there's no one else there to hear you scream. But it works either way. So we have these condensations and rarefactions, and the distance between them is like any other wave between any successive equal points. We call that the wavelength of the sound. So that would be what we'd associate with the wavelength on this pressure wave. So sound is indeed a pressure wave. It's got an amplitude, which is our maximum point of pressure change. It's got an angular wave number, k, in front of its spatial component x, and an angular frequency, omega, in front of its time. So maximum amplitude, angular wave number, angular frequency, like any other wave that we've talked about, say, in chapter 16. Your book spends 3 or 4 pages on this subject, but that's basically what the conclusion is. Sound is a wave, amplitude, wave number, and angular frequency, like any other wave. We define the power of a sound wave as its energy transmitted per time. As we're transmitting energy, if we do that over time, we can associate power with that, like power with anything is energy per time. But we're also interested in another aspect of this energy transfer. The power exerted per cross-sectional unit of travel is called the intensity. So as this power is being exerted over a cross-section, that is the intensity of the sound. If it's more area, it's going to be less intense because it's going to be diluted over that more area. If it's less area, it's going to be more intense. So intensity is power per area. Let's try this out. The area of a typical eardrum is about 5 times 10 to the minus 5 square meters. Calculate the sound power, the energy per second, incident on an eardrum at the threshold of hearing, which is the lowest intensity that a normal human being can discern. It's 10 to the minus 12 watts per meter squared. So what is the power on the eardrum at that intensity? Intensity equals power per area, so equivalently, power should equal intensity times area. And on the eardrum, that would be a intensity of 10 to the minus 12 watts per meter squared. Area of the eardrum is 5 times 10 to the minus 5 square meters. So that is a power of 5 times 10 to the minus 17 joules per second, or watts. So that is a very small signal that your eardrum would be able to discern. What is the power at the intensity of the threshold of pain? The threshold of pain is an intensity of 1 watt per meter squared, and that is the intensity at which we would start to cause pain on our eardrum. If our eardrum were to experience that kind of intensity, it would start to do damage. So that is the threshold of pain, and that would correspond to a power on the eardrum of 1 watt per meter squared times the area of the eardrum, 5 times 10 to the minus 5 meters squared, or 5 times 10 to the minus 5 watts. So we can see for the normal human range of what we can just barely discern at the threshold of hearing to what we would want to listen to at our maximum, the threshold of pain, there are 12 orders of magnitude between those and those powers. So we have 12 orders of magnitude that we can discern with the human ear. If we had a power source emitting sound, it would be, let's assume it's emitting sound in all directions. So this power is being transferred over the area in a sphere of radius r, if we are some distance r away. And it's being transferred, let's say, equally in all directions. So we're not necessarily gaining all the power in our direction. So that means that the intensity would be distributed over the surface area of a sphere of radius r. We can think of the intensity as power per area, but in this case it's power over that surface area, power over 4 pi r squared. So if we were 1 meter away, we would get a certain amount of power over the area of a sphere of 1 meter. But if we were 2 meters away, the area of that sphere is 4 times as much. So the intensity would only be 1/4 as much because that power is distributed over this greater area. So the further we get away, the intensity drops off as your distance squared. If we were 3 meters away, then we have 9 times the area that the same power is being distributed over, and hence we would only get 1/9 as much where we happen to be. So the intensity is inversely proportional to the distance squared. That concludes the first section of the lectures. The next section we're going to go on to is to discuss decibels.